using these relations, we can draw the information curve like this way. So difference between SP and SP bar A. So before the halfway point, the detected information is very negligible, but as time goes on, gradually information increases. So if we are observing black hole around this stage, then we can detect that black hole begins to emit information. So if SA, so this curve, SA is proportional to the black hole area, as Bekenstein said, then information will come out when the initial area decreased to its half value, and this time scale is called the information retention time. So after this time, information begins to come out. So let me say that initially we were here. So, there was very limited information, and as time goes on, black hole emits, and let's say that black hole approaches the halfway point. So it approaches halfway point, then still black hole is very large. So still black hole will emit Hawking radiations. However, so still it's very large, and Hawking radiation will emit, but such radiation should contain the information. So if SA proportional to black hole area, then Hawking radiation should contain information. However, Hawking radiation, according to Hawking's calculation, Hawking radiation seems only depends on mass, angular momentum, and charging. That is the really serious problem. So it's a paradox. Hawking radiation should contain information, but Hawking radiation should not contain information according to Hawking's calculation. That is the origin of the paradox.
What does this middle point mean? Because A can be anything.
Yeah.
What does halfway mean? Because A can be anything. So is there a definite A that applies here? I can iterate this and.
So you mean the system A and B can be anything, but if SA is proportional to event horizon area, then we can apply the black hole physics for this curve. So
I'm just saying, even for this page argument, is there any absolute meaning of A? Because by the argument, you can emit information before reaching this half point, but the half point is not defined, so you can always do this then.
No.
So I don't understand the argument.
No. Initially, if the
what is initial mean? What is initial?
So, for example, if a gravitational collapse makes a black hole, and if we evaporate after the formation, then the formation point is the initial entropy. And from the formation of the black hole, it begins to evaporate. Then we can define the halfway point.
But if we're talking about primordial black holes, it's not your usual concept of collapse, right?
Right.
So again, initially it's still defined.
Yes. So for primordial black holes, I guess it can be more subtle.
So I'm just saying that I don't understand this argument. Why is there a middle point? Because A can take on any value in this argument.
However, whatever is its value, this half point is relative to that starting value. And since Hawking evaporation is approaches zero if the initial mass is huge, so it is practically possible to define the initial condition without worrying about how to well define its initial mass.
Yeah, but if you iterate the argument, it means I can extract information until the very end.
Well, yes, but halfway meaning halfway from its starting point.
I don't understand what starting point means.
In the case of collapsing, gravitational collapse.
Has already collapsed. So.
No, the gravitational collapse to form a black hole. When that happens, when that black hole finally appears, that's the starting point.
Do we really understand primordial black holes are big?
Yes, I was commenting on the.
So what is?
I was commenting on the gravitational collapse.
Any A from primordial, right? So
Well, primordial, if we think in terms of, say, Planck era, Planck scale, as Gross, Perry, and Jaffe has demonstrated, the probability of generating primordial black hole is exponentially suppressed if the black hole mass is much larger than the Planck mass. Okay, this is a well-known paper in 1983. So that means the primordial black hole typically will have masses around the Planck mass, maybe at most a few times more. Now, but whenever that was generated, say at the Planck era, 10 to the minus 43 seconds, and that's where you define its initial mass. There's a time, right? So you can determine what the mass it was at that time, and this page limit is half of that.
Excuse me. Is the point on this page that the Hawking radiation or the entropy transfer is not equivalent to information?
I'm sorry. So from this point, this halfway point.
What is the main point on this slide?
Yeah. So the main point is that if it is unitary, then and also if level entropy proportional to the area, then Hawking radiation should contain information after the halfway point. But according to Hawking's calculation, Hawking radiation really depends on less angular momentum charge. So this is quite paradoxical because this doesn't have any quantum information.
Is the paradox in the dependence on the J and Q?
So in fact, Hawking radiation should be described by more quantum information, not only M, J, and Q. Some three numbers.
Okay, I agree. So I still don't see the paradox.
Yeah, so Hawking radiation should contain information according to this argument.
Yes.
Then Hawking radiation should be a function of not only M, J, Q, but also some quantum numbers.
That's right.
But according to Hawking's calculation, it is only a function of the M, J, and Q.
Okay.
That is the paradox.
But Hawking says it's a function of M, J, and Q.
Yeah, right.
But there is no paradox.
It's certain.
No. Look, I think to exaggerate, if one throws Donghan's USB into the black hole, that USB is only a few grams weight. So this black hole changes mass from m plus delta m. Now, but that USB has 2 gigabytes of information. Now, so this black hole, if everything is preserved, then should, in principle, increase its information by that much. However, this m plus delta m, according to Hawking, is evaporating purely in the black hole sense. And so this evaporation only recognizes the total mass, the m plus delta m, without worrying about how much information is carried. And therefore, this Hawking radiation, in a sense, is too simple. If according to this diagram, it should carry out more information by this Hawking evaporation. Otherwise, in the end, the numbers do not add up.
Okay, from this plot, how do you see that there are numbers that do not add up?
Because from this diagram, you expect that the information should go up like that towards the end of the black hole life.
That's right.
Yeah. Yet on the other hand, the only mechanism that can reduce the black hole mass was through Hawking radiation,
That's right.
which only tells you 3 informations: the mass, the J, and the Q. And that's not sufficient.
Yeah.
Excuse me, just make sure. From discussion of entropy, just forget the Hawking radiation. From discussion of entropy, entanglement entropy must be lower than this total.
Yeah, right. So mutual information is always positive. So this is the famous paper about the information velocity, 1976 by Hawking, and these circles are keywords. So first the keyword is singularity. So always break by the singularity, and this makes the hidden surfaces called event horizon. And even though there is event horizon, but if a black hole is forever, then maybe information is always there. But problem is that black hole will evaporate and disappear. And then it's not easy to, maybe impossible to define the S matrix that can connect unitarily from in state to out state. So this is the reason why he said something about breakdown of predictability. So if there is S matrix, then we can predict something in terms of probability. But if there is no S matrix, then there is no way to predict after the formation and calculation of the black hole. And this may mean that there is no quantum gravity. So this is the information loss problem, the famous paper of Hawking. So gravitational collapse forms a singularity in event horizon. And after evaporation, the black hole will disappear, and we should paste the same diagram, Minkowski diagram. So S matrix defined from in state to out state. But in between out state and in state, there is something unclear point. So because of here, the information of the star interior completely disappeared, and only information of the black holes, let's say MJQ, determines the future evaporation. So this is the origin of the information loss problem. So if Hawking radiation is totally thermal, then we lost the information set to less charge and environment. This implies a violation of unitarity. And if some quantum theory is not unitary, then it is not a well-defined quantum theory. So maybe quantum gravity does not make sense. That is the really serious problem of quantum gravity information loss problem. And however, we hope predictable and sensible theory of everything, whatever it is, string theory or quantum gravity or any theory. So this is the reason why information loss problem is very difficult, but very important to resolve toward the consistent theory of quantum gravity. So from the, if time permits, let me very briefly show the candidates of resolutions as a bird's eye view. So if time is not available, then maybe I have to say up to this candidates of resolutions. So this is a bird's eye view. So I drew as a flow chart, but maybe let's briefly say step by step. So first, the input is the information with parameters. Then let's say first question: does the information conserved or not? If you say no, so if there is information loss, then we receive the information loss, and there is no estimate. And so this was the opinion of Hawking in 1976. But a few years later, thanks Peskin Susskind, this people in 1980 discussed that this information loss will cause disaster in our universe. So if there is information loss, then from the vacuum, particles can be created. Then particles are created, and our universe will be hotter and hotter, and temperature will indefinitely increase. So it's a real disaster. It should not happen. So this is the discussion of Peskin Susskind. And there was some controversy between Hawking's Peskin Susskind and so on. But nowadays, the mainstream is following the yes direction. I think that because the reason is Baldassin's the famous paper ADS-CTP. So if we trust ADS-CTP, then ADS is gravity physics, and CFT is field theory at boundary, and CFT is always unitary because it is field theory. And then since there is a correspondence, the gravity physics should be unitary manifestly. That was the interpretation of Baldassin and Witten in 1998 paper. So this is very reasonable and successful result from string theory. So nowadays many people tend to follow this yes direction, but of course there are some limitations. First, ADS-CFT is not exactly proven statement. Secondly, ADS-CFT cannot make real constructive way how can information comes out. way that it should be military. And thirdly, we are now living in crystal space, not a anti-crystal space. So maybe there is some subtle issues, but maybe also it's fair to say that it's very reasonable to trust the yes direction. So if we say yes, then if we now let's ask this question: does Hawking radiation carry information or not? If we say about yes, according to Page's argument, then we should reach the idea of so-called black hole complementarity. So it was formally suggested by Susskind scholars in 1993. But before this paper and around this paper, lots of mainstream physicists suggested this idea. One is Gibson's the membrane paradigm, and the other is Tufte's holographic principle and complementarity. So in this paper, Tufte commented about complementarity in the black hole physics, although it was not exactly the same as Suskind's complementarity. And he said something about complementarity. And the famous Stromin-Zobakas paper, they introduced the deep brain picture. And according to Kallan and Maldasnas, this paper, they said that the deep brain picture is very similar as the membrane paradigm, as well as the variable complementarity. And lots of people constructed this idea. Polchinski, Presky, lots of people did it. And here is my paper. So a few years ago, I and my colleagues argued that, in fact, black hole complementarity seems not consistent because of some thought experiment. And our papers were not cited very much, but in 2 years ago, famous paper was appeared, Almeida, Marov, Polchinski, and Sally. Now we say that AMPS. So, according to AMPS paper, again, black hole complementarity is inconsistent. And then what is the consequence? AMPS thought that we have to radically modify black hole physics, and black hole horizon should be surrounded by some fuzzy sphere, so-called firewalls. They introduced the firewall, and there are lots of controversies.
I'm sorry, what's the essence of the black hole complementary picture?
Yes, maybe if time permits, then I want to say.
Okay.
And when so if we say that it is no, so maybe if you believe that complementarity is inconsistent, so if we say this direction, then the third question is this: does information retained by something another object rather than Hawking radiation? So if we say yes, then we follow so-called briefly defined the remnant picture. So there are lots of references. I selected some important one, and this paper was written by Professor Chen, and also there are lots of issues. And in this black hole remnant scenario, information can be stored in very Planck scale object, or after resolving the singularity, information can be recovered from such a quantum recognition effect, or information is retained by internal structure, for example, bubble universes, and so on. Or there are some other ways, for example, by using some detailed quantum entanglements between ingoing Hawking radiation and outgoing Hawking radiation, or by assuming some detailed information theoretical things inside the black hole. So there are some ideas, but I cannot say the details, but maybe the conclusion seems that these are not quite generic. So these are still viable, but to apply for every black hole, it seems not very general, and we have to assume some very detailed things to make these things. So in our Professor Chen and Dr. Ong and me wrote a recent review paper, and in this paper we discussed some details. So just a very brief outline.
So in this view, is there a direction that the Hawking radiation does not exist?
I believe that Hawking radiation exists,
Okay.
but I don't know how to, if it is true, then how to prove that there is no Hawking radiation. Yes. So I'm not sure the time is limited, but let me very quickly say that what is black hole complementarity, what is the counter argument. So black hole complementarity basically says that the principle of black hole complementarity says that there is no observer sees violation of natural laws. So for the inferring observer, so inside the event horizon, general relativity should be good description. That is first doctrine of black hole complementarity. Secondly, for asymptotic observer, unitary semi-classical quantum field theory. So simply Hawking's calculation should be a good description. And both observers, inferring and asymptotic observers, both are complementary. So complementary means that inferring observer may see something and asymptotic observer may see something, and they are not very consistent, but they are complementary, like wave and particle duality. So for any observer, unitarity, quantum mechanics and its consequences, no cloning theorem and so on should be satisfied. This is the basic idea of complementarity. So let's say what is going on. So this is the black hole causal structure, event horizon, and singularity. And let's send a bit of information to the black hole. So I sent this bit of information. And according to the Page's argument, after the page time, information should be attached by Hawking radiation outside the event horizon. Then this is somehow strange because for a certain space like hypersurface, information is duplicated. One is here and the other is here. So information seems to be duplicated. So let's say that there is an observer who approaches the event horizon and detects Hawking radiation. And fortunately falls into the black hole. And if also fortunately if this inferring information is scattered to the outgoing direction, then before touch the singularity, this observer can see both of information, both of duplicated information. So if it happens, then for this observer, physical laws, unitarity is inconsistent because the information is duplicated and really observed. Then black hole complementarity is inconsistent. So this experiment was already considered by CTS-NTU in 1994, but at that time they said that this was impossible because the time difference delta t, so after simple calculation, delta t should be exponentially short, exponential minus m squared. Then this means that to send a bit of information, we have to rely on the uncertainty relation. Delta A, delta T is order of h bar. Then the required energy to send a bit of information to outgoing direction should be exponential m squared. This means that to send a bit of information to outgoing direction for duplication experiment, the required energy is much larger than the black hole mass itself. So it shouldn't happen. So if this inequality is satisfied, then this makes sure that black hole complementarity is consistent. And after a few years later, Hayden and Preskey said the other time scale is much shorter than the information retention time. And after some calculations, we obtained this marginal relation. So even though Hayden Preskey's time scale is true, black hole complementarity seems that it's marginally safe. That was the conclusion up to 2007. But this is a very quick summary of my paper. So such a discussion that delta t is exponential minus m squared is implicitly assumed that the number of scalar fields that contribute to Hawking radiation is, for example, n equals 1. Then in this case, then delta t is exponentially short. But what happens if the Hawking radiation number of scalar fields that contribute to Hawking radiation is very large number, and as well as we can change the mass of black hole by this factor. So this is nothing strange. It's just a number, and we can scale compared to this n in terms of Planck scale. And then causal structure is the same, but Planck scale unit length becomes smaller and smaller. And because of this, we obtain some scaled n factor. Even though so this is invariant, but this square root n factor appears. Then after some calculations, I will follow the technical details, but eventually, let's say that this inequality is the consistency condition for black hole complementarity, but if n becomes larger and larger, then this inequality can be violated. So this is the reason why I'm saying that this large n argument is a counterexample of black hole complementarity. And so a few years later, AMPS discussed that black hole complementarity is still inconsistent. So maybe this is quite conceptual things. So I will very quickly say this, and if you are interested, then please see this slide later. So there are three parts. One is earlier part before the page time, earlier part of Hawking radiation before the page time. The other part is later part of Hawking radiation after the page time, and the other part is the ingoing counterpart of Hawking radiation. So let's say that it is F. Then using these three subsystems, we can calculate. We can calculate the entropies. So these two inequalities are just inequalities satisfied for all systems, strong sub-additivity and sub-additivity. And by calculating some things, it seems that some entropy component becomes negative. Every entropy should be positive, but it seems that after some assumptions of black hole complementarity, it seems to be negative. So it is inconsistent for this including who detect E, L, and F at the same time. This is the essential point of AMPS document. In conclusion, AMPS can be applied for various cases, and large n rescaling of my idea is also applied for some systems. So I think that there is no further doubt on the inconsistency of black hole complementarity. So black hole complementarity is inconsistent enough, and we have to find some alternatives for this idea. And one short comment is that according to AMPS, they want to resolve this paradox by modifying some conservative assumptions. Then they concluded that ingoing observer should violate general relativity around the horizon scale and should see so-called firewall around the event horizon. But up to now, there is no mechanism to create a firewall, and it's very subtle. So it's still controversial, and I don't know what is the conclusion what we have to say. So let me go back to this slide again. So I believe that we should not go this way. Then we should go here, and either we say yes or no. So maybe very recently I'm working on this final part. So maybe I cannot say the details of this idea, but if we have time, then I want to say this idea. So it's something about path integral approach, and something about Hawking's recent idea that I was wrong and information should be conserved, and it is related to Hartree wave function and path integral, instant and so on. So I'm interested in this approach, and I hope for the next time I want to say more details about this way. That's all.
Further questions?
Do I understand you correctly that the idea with the firewall is still alive?
I cannot say that firewall is ruled out, but what I can say is that if there is firewall, then it should be observed by the outside observer. So I mean, firewall should be outside the event horizon. Then the question is, can we accept this? So if firewall is such as naked singularity, for example, then can you accept such a concept that is outside the event horizon? So maybe it's controllable.